There's something almost unbearable about the idea of a universe without rules. Imagine looking up at the night sky and seeing not patterns, not predictable movements, not the reassuring return of familiar constellations, but only chaos. Random lights appearing and disappearing without reason. The sun rising when it pleases, the moon changing its mind about its phases. For thousands of years, humans looked up and saw order, sensed that there must be rules governing everything, but couldn't quite grasp what those rules were or write them down in a language that would hold true everywhere for all time. Then one man, born on a winter day in a stone manor house in the English countryside, found that language. He didn't just describe the universe. He explained it. If you're finding value in this journey through history, if these stories help you drift toward rest while expanding your understanding of our world, consider subscribing to the channel and leaving a like on this video. It helps others discover these explorations into the past, and it lets me know that this work matters to you. The year is 1642, Christmas Day by the old calendar still in use in England, though most of Europe has already adopted the Gregorian system and would call it January 4th, 1643. In a modest stone manor in the hamlet of Woolsthorpe in Lincolnshire, a tiny, premature infant enters the world so small that, as his mother would later say, he could have fit inside a quart pot. His father, also named Isaac Newton, will never meet him. The older Isaac died 3 months earlier in October, leaving behind a pregnant widow, some land, a flock of sheep, and debts. The baby, arriving far too early, is not expected to survive the night. 2 women are sent to a nearby estate to collect medicine or perhaps just to fetch someone to witness the child's brief existence. They sit down on their way, expecting that by the time they arrive and return, there will be no reason to hurry. But the infant, against all reasonable expectation, continues breathing. He survives that night and the next and the one after that. His hold on life is tenuous, his body weak, but something in him refuses to let go. The manor house at Woolsthorpe is not grand, but it's solid, built of local limestone, 2 stories, surrounded by fields and orchards. In winter, the Lincolnshire landscape turns gray and brown, the trees bare, the sky low and heavy. Wind comes across the fields without obstruction, carrying the smell of wood smoke from distant cottages. Inside, the rooms are cold except where fires burn, and fires consume precious fuel that must be carefully rationed. The infant survives his first winter wrapped in wool, kept near the kitchen hearth, the center of warmth and life in the house. His mother, Hannah Ayscough Newton, 20 years old and now a widow, tends to him with whatever mixture of love and grief and exhaustion fills the hearts of women who give birth alone in the middle of winter in the middle of a civil war. England in 1642 is tearing itself apart. King Charles I and Parliament have moved from disagreement to open conflict. Armies are forming, choosing sides, preparing to fight over questions of royal power, religious authority, taxation, and the fundamental nature of governance. Lincolnshire is somewhat removed from the early battles, but the war is everywhere in the background, a constant source of anxiety and disruption. Trade suffers, taxes increase, young men disappear to join one army or another. For a widow with a newborn and property to manage, the future must seem precarious. Hannah has her own family, the Ayscoughs, who are slightly better established than the Newtons, with connections to education and the church. But she's alone in the manor with an infant who nearly died and may still die at any moment from any of the 1,000 dangers that claim children in this era. The baby grows, slowly, remaining small and fragile. He learns to grasp, to focus his eyes, to make sounds. The world he perceives is limited to the rooms of the manor, the faces of his mother and perhaps a servant, the play of firelight on walls, the sounds of wind and sheep and the creaking of old wood. There are no signs yet of what he will become, no indication that this particular child, survivor of a difficult birth in a difficult time, will someday explain how planets move and why apples fall and what light is made of. He's just a baby, underweight, fatherless, living in a stone house in the countryside while the nation bleeds. 3 years pass. Isaac learns to walk, to speak, to recognize the rhythms of the household. His mother remarries in January 1646, when Isaac is just past his 3rd birthday. The man she marries is Barnabas Smith, the rector of the church in North Witham, a village about 1.5 miles from Woolsthorpe. Smith is 63 years old, wealthy by local standards, established, and in need of a wife to manage his household. For Hannah, the marriage offers financial security and social respectability. For Isaac, it offers abandonment. Barnabas Smith has no interest in raising another man's child, and the arrangement is clear. Hannah will move to North Witham to live with her new husband, and Isaac will remain at Woolsthorpe with his grandmother, Marjorie Aisco. At 3 years old, Isaac watches his mother leave. She walks away down the lane to a new life, a new husband, and soon new children, half-siblings who will receive the attention and affection that he does not. The psychological wound of this abandonment is impossible to measure precisely, but it cuts deep. Isaac is left in the care of his grandmother, a woman who provides for his physical needs but who cannot replace his mother. The manor feels emptier. The rooms echo. At night, the child must wonder why he was left behind, why he was not enough to keep his mother with him, whether he is somehow defective or unworthy. In later years, when Isaac Newton compiles a list of his sins, written in a private notebook in a kind of self-examination required by Puritan religious practice, one entry will stand out with particular force: threatening my father and mother Smith to burn them and the house over them. This rage, this violent fantasy, speaks to the depth of his resentment. He does not threaten his mother alone, but his mother and her new husband together, the couple who chose each other and left him. Days in Woolsthorpe pass slowly for a child alone. His grandmother manages the property, oversees the farm work, maintains the household, but she is old and her energy is limited. Isaac spends time by himself, wandering the property, observing animals, watching the work of the farm from a distance. He's not expected to labor, not yet. He's too young and too small. Instead, he watches. He sees sheep being sheared, crops being planted and harvested, fences being mended, tools being repaired. He notices how things work, how a gate swings on its hinge, how water flows in a ditch, how shadows move across the ground as the sun crosses the sky. There is an orchard on the property, apple trees that bloom in spring and bear fruit in autumn. In winter they stand bare, their branches forming complex patterns against the gray sky. Isaac looks at them, and perhaps even then, some part of his mind is beginning to see patterns, to notice that there are regularities in the world, even if he doesn't yet have the language to describe them. He begins to build things. With scraps of wood and simple tools, he constructs little models. Windmills that actually turn in the breeze, water wheels, sundials. These are not toys exactly, or not merely toys. They are investigations, attempts to understand and replicate the mechanisms he sees around him. A windmill is a machine that captures invisible wind and transforms it into visible motion. How does that work? What angle do the blades need to be? How is the motion transferred from the blades to the grinding stones inside? Isaac doesn't have formal instruction in mechanics or engineering. He figures things out by observation and trial and error. When something doesn't work, he adjusts it until it does. There's a satisfaction in this, a sense of control and competence that must be especially precious to a child who has so little control over the larger circumstances of his life. The household operates on the rhythms of agriculture and the Christian calendar. Sundays mean church, sitting through long sermons, absorbing the Puritan emphasis on sin, salvation, and the scrutiny of one's own soul. Weekdays mean chores, lessons if anyone is available to provide them, and long stretches of unstructured time. Isaac learns to read, probably taught by his grandmother or perhaps by a local clergyman. Reading opens a new world. There are not many books in Woolsthorpe, but there are a few primarily religious texts: the Bible, sermons, devotional works. Isaac reads them, absorbing not just the content but the idea that knowledge can be preserved and transmitted through written words, that people in the past have recorded their thoughts and that those thoughts can be accessed by anyone who can read. He is a solitary child, not by choice initially but by circumstance, and solitude shapes him. Other children in the area are the sons and daughters of farmers and laborers, and there's little opportunity or reason for them to spend time with the young heir of Woolsthorpe Manor. Isaac is set apart by class, by his father's early death, by his mother's absence, by his own temperament. He doesn't develop the easy social skills that come from constant interaction with peers. Instead, he develops the ability to entertain and occupy himself, to find interest and challenge in solitary pursuits. This will serve him well later, when he needs to spend months or years working alone on problems that no one else understands or cares about. But in childhood, it must often feel like loneliness, like being on the outside of a warmth he can see but not reach. Seasons pass, marked by the changing work of the farm, the lengthening and shortening of days, the cold of winter and the brief warmth of summer. Isaac grows taller, though he remains slight, never developing the robust physical strength of boys raised to farm labor. His hands learn to manipulate small tools and objects with precision, but they do not develop the calluses of a plowman. His mind, meanwhile, is learning to manipulate something else. Problems. How to make a mechanism work, how to mark time using the sun's shadow, how to predict where that shadow will fall at different times of day. These are mathematical problems, though he doesn't think of them that way yet. They are simply interesting challenges, puzzles that have right answers if only he can figure them out. His mother remains 1.5 miles away in North Witham, living a separate life. She has children with Barnabas Smith, a son, Benjamin, and 2 daughters, Mary and Hannah. These are Isaac's half-siblings, but he is not raised with them. Occasionally there may be visits, brief and awkward, where Isaac sees his mother in her new role, attending to her new children, existing in a world that does not include him. Or perhaps there are no visits at all. Perhaps the separation is complete. Either way, the message is clear. He has been set aside. Years later, when Isaac Newton is an old man, famous and powerful, he will still be unable to form close personal relationships. He will never marry, never seem comfortable with physical or emotional intimacy, never develop friendships that are warm and easy. The roots of this isolation are here, in these early years at Woolsthorpe, in the absence of his mother and the long quiet days with his aging grandmother. In 1653, when Isaac is 10 years old, the situation changes suddenly. Barnabas Smith dies. Hannah is a widow again, now with 3 young children in addition to Isaac. She returns to Woolsthorpe, bringing Isaac's half-siblings with her. The manor house, which had been quiet and sparsely populated, suddenly fills with people, with noise, with a chaos of young children. Isaac, who has had years to adjust to being alone, now must adjust to not being alone, to sharing his home and his mother with others who have, in his eyes, already taken her from him. The return of his mother after 7 years does not repair the wound of her leaving. If anything, it may deepen it, because now she is present but distracted, her attention divided among multiple children, her energy consumed by the practical tasks of managing a household and a property that has grown more complex. Hannah takes over the management of the Woolsthorpe estate, which now includes not just the original property but also the holdings that came with Barnabas Smith. There is more land, more income, more responsibility. She is a capable woman, pragmatic and determined, but she is also stretched thin. Isaac is expected to help, to take on responsibilities around the farm, to begin learning the work that will presumably be his future. But he has no interest in farming. He does not want to tend sheep or mend fences or oversee the planting of crops. His mind is elsewhere, occupied with his own projects and thoughts. When he is sent to watch the sheep, he brings a book and reads instead of watching, and the sheep wander into neighboring fields causing complaints. When he is supposed to be helping with market day, he disappears to tinker with some mechanism or to solve some problem that has caught his attention. He is not rebellious in the sense of openly defying authority. He simply absents himself mentally from the tasks at hand, retreating into his inner world. His mother and grandmother must find this frustrating. Here is a boy who should be preparing to take over the family property, who should be learning the practical skills that will allow him to maintain and increase the family's modest wealth. And instead he is building toy windmills and scribbling in notebooks. It looks like irresponsibility, like daydreaming, like a failure to grasp the realities of life. They cannot see what he is actually doing, which is laying the groundwork for a different kind of future entirely, one where his value will not be measured in acres or sheep but in ideas and understanding. During this time, Isaac attends the free grammar school in Grantham, a market town about 7 miles from Woolsthorpe. This means living in Grantham during the school term, lodging with the family of an apothecary named Clark. The grammar school provides education in Latin, Greek, arithmetic, and religion. It's a step up from whatever informal education Isaac received in Woolsthorpe, and it brings him into contact with other boys, with teachers, with a wider world beyond the narrow boundaries of the farm. At Clark's house, he is exposed to books, to the tools and ingredients of the apothecary trade, to conversation about matters beyond agriculture. Clark has a stepdaughter, Miss Story, and there are later reports that Isaac formed some kind of attachment to her. Though the details are vague in the relationship, whatever it was leads nowhere. It may have been an early, awkward, adolescent infatuation, the kind of feeling that is intense in the moment but leaves no lasting mark. Or it may be exaggerated or invented by later biographers looking for human interest in the life of a man who seemed to have little interest in human connection. At school, Isaac is competent but not initially outstanding. He learns what is taught, masters Latin grammar, reads classical authors, works through mathematical problems. But he also continues his own projects, building models, drawing, filling the margins of books with diagrams and notes. There is a story, possibly apocryphal but repeated often enough to have become part of the Newton legend, that he is bullied by a larger boy, challenged to a fight, and despite his smaller size, defeats the bully and then, not content with physical victory, makes a point of surpassing him academically as well. Whether or not this specific incident occurred, it captures something true about Newton's temperament: a fierce competitiveness, a refusal to be dominated, a drive to prove himself superior. In 1658, when Isaac is 15, his mother decides that his formal education has gone on long enough. She calls him home to Woolsthorpe to take up his responsibilities as the man of the estate. She has managed alone for several years, but Isaac is now old enough, in her view, to step into the role his father's death left vacant. Isaac returns to Woolsthorpe, and for several months, there is an attempt to make him into a farmer. He is sent to markets to sell produce and livestock. He is given oversight of workers and land, and he is utterly hopeless at it. He does not pay attention to prices, often selling at a loss or forgetting to sell at all. He does not supervise the workers who take advantage of his inattention. He continues to read books and build models when he should be negotiating deals or inspecting fields. He is present in body but absent in mind, and it becomes painfully clear that forcing him into the mold of a gentleman farmer is not just impractical but impossible. His uncle, William Ayscough, a clergyman and a graduate of Cambridge, recognizes that Isaac's talents lie elsewhere. So does John Stokes, the headmaster of the Grantham School, who has seen Isaac's abilities. Both men urge Hannah to let Isaac return to school and prepare for university. Hannah resists at first. University is expensive, and it means years more without Isaac's help at home, and there's no guarantee of any practical return on the investment. But eventually, she relents, perhaps recognizing that Isaac is simply not suited for the life she had envisioned for him, perhaps persuaded by her brother's arguments, perhaps exhausted from trying to force an incompatible piece into the wrong puzzle. Isaac returns to Grantham, spent several more months preparing, and in June of 1661, at the age of 18, he arrives at Trinity College, Cambridge, to begin his formal university education. Cambridge in 1661 is emerging from the turbulence of the Civil War and the interregnum. The monarchy has been restored. Charles II is on the throne. The Church of England is being re-established. The university itself had been disrupted during the war years, with some scholars fleeing, some imprisoned, some ejected for political or religious reasons. Now there is an effort to return to normalcy, to rebuild the colleges, to restore the curriculum. But the curriculum being restored is in many ways outdated, still focused on Aristotelian philosophy and scholastic logic, still teaching a view of the natural world that had been dominant for centuries but was increasingly under challenge from new thinkers across Europe. Trinity College is one of the largest and wealthiest of the Cambridge colleges, founded by Henry VIII, with an impressive great court surrounded by stone buildings, a chapel, a library, halls where students eat and scholars debate. Isaac arrives as a subsizar, a category of student below the regular students, boys who work as servants for wealthier students in exchange for reduced fees. Subsizars empty chamber pots, serve meals, run errands. It's a humiliating position for someone who is technically from the landowning class, but the reality is that Isaac's family, while not poor, does not have the resources to support him as a regular student. And being a subsizar is better than not attending at all. He endures the servitude, the reminders of his lower status, the small indignities. It must sting, must remind him again that he is an outsider, not quite fitting in, dependent on the tolerance and charity of others. But he accepts it because Cambridge offers something he cannot get anywhere else: access to knowledge, to books, to teachers, to ideas. The official curriculum is centered on Aristotle, studied through commentaries and disputations. Students are expected to learn logic, rhetoric, ethics, physics as Aristotle understood it, metaphysics. They attend lectures, participate in formal debates, work toward their degrees through a system that values adherence to established doctrine and the ability to argue positions using approved methods. This is the education that has been provided for generations, the bedrock of European intellectual life. But it's also increasingly inadequate. Aristotle's physics, which explains motion and change through concepts like natural place and essential form, cannot account for the new observations being made with telescopes and experiments. His cosmology, with the Earth at the center of nested spheres, has been undermined by Copernicus, Kepler, and Galileo. A revolution in understanding is underway, but the university curriculum has not yet caught up. Isaac attends the required lectures, fulfills his obligations as a subsizar, and begins to read on his own. He discovers Descartes, whose philosophical and mathematical works offer a radically different approach to understanding nature. Descartes proposes that the universe operates like a machine, governed by laws that can be described mathematically, that matter is simply extension and motion, that the old categories of form and purpose are unnecessary. Isaac also encounters the work of Galileo, who demonstrated through experiment and observation that falling bodies accelerate at a constant rate, that the path of a projectile is a parabola, that the moons of Jupiter orbit around Jupiter, not around Earth. He reads about astronomy, about optics, about the new mechanical philosophy that sees the universe as a vast clockwork mechanism rather than a living organism with purposes and tendencies. This reading is not assigned by his tutors. It's self-directed, pursued in the hours when he is not serving meals or attending official lectures. Isaac keeps notebooks where he copies out passages, works through problems, records his own thoughts. One of these notebooks, which survives, has a title page that reads Questions Quidem Philosophicae, or Certain Philosophical Questions. It's filled with notes on topics that interest him: motion, matter, color, the nature of light, the void, atoms. The entries reveal a mind that is questioning everything, that takes nothing on authority, that wants to understand how things really work rather than simply memorizing what Aristotle or anyone else said they should be. This is the beginning of the intellectual independence that will define his career. He also encounters mathematics in a more serious way. The standard curriculum includes some arithmetic and basic geometry, but Isaac goes beyond this, teaching himself more advanced topics. He studies Euclid's Elements, the foundational text of geometry, working through the proofs. He discovers the work of William Oughtred, who wrote on algebra and invented the slide rule. He explores the geometry of Descartes, which shows how to represent geometric shapes using algebraic equations, a unification of two branches of mathematics that opens up new possibilities. Mathematics begins to reveal itself not just as a tool for calculation but as a language for describing relationships, patterns, structures. It's abstract, precise, beautiful in its own way. And it's powerful because mathematical relationships can be manipulated, transformed, used to derive new truths from old ones. Cambridge is also a place of social hierarchies and personal relationships, though Isaac seems largely outside of or uninterested in these aspects of university life. He does not form close friendships, does not join in the drinking and socializing that occupies much of student life, does not distinguish himself in the formal academic disputes and examinations. He is focused, intense, self-contained. His room, when he has one, becomes a workshop and study, filled with books, papers, instruments he has constructed or modified. He learns by doing, by experimenting, by thinking through problems until they yield. His mind is restless, always pushing forward, always asking the next question. In 1665, after 4 years at Cambridge, Isaac receives his bachelor's degree. It's an unremarkable achievement, granted more or less automatically to students who have fulfilled the requirements and caused no major problems. There is no indication at this point that Isaac Newton is anything other than a capable but not exceptional student, someone who will likely return to Lincolnshire to manage his family's estate, perhaps serve as a local clergyman, live a quiet and forgettable life. The university keeps records of its students, and Newton's name appears in those records without any special distinction. If he had stopped there, if his life had ended or taken a different path, he would be completely unknown to history. But he doesn't stop. He cannot stop. Something drives him forward, some combination of curiosity and ambition and an almost desperate need to understand. In the summer of 1665, the bubonic plague, which has been simmering in Europe for years, breaks out in London with terrifying intensity. By July, 1,000 people a week are dying. By August, it's thousands per week. The disease spreads through the crowded, unsanitary city, indiscriminate in its victims, killing rich and poor, old and young. Those who can flee do so, abandoning the city for the countryside. The infection spreads along trade routes, appearing in towns and villages. By August it reaches Cambridge. The university authorities, recognizing the danger, close the colleges. Students and fellows are sent home to wait out the epidemic. Isaac, who has just graduated but was planning to continue at Cambridge as a scholar, packs his books and papers and returns to Woolsthorpe. He will remain there in the isolation of the Lincolnshire countryside for the next 18 months. And in that time, alone in the manor house where he was born, cut off from teachers and fellow students and the normal routines of academic life, he will experience a period of creativity and insight so concentrated and profound that it will later be called his annus mirabilis, his miraculous year. In truth, it's more like 18 miraculous months, but the label sticks because what happens during that time seems almost impossible, a flowering of genius that has few parallels in history. The England Isaac returns to in the summer of 1665 is a nation under siege by invisible forces. The plague is spreading and no one knows how to stop it or even really what causes it. The prevailing medical theory involves bad air, miasmas, imbalances of humors. Some people think it's divine punishment for sin. Others suspect it spreads through contact with infected individuals or their belongings. The actual mechanism, transmission by fleas living on rats, is completely unknown. The response is a mixture of quarantine, prayer, and panic. Infected houses are marked and sealed, their inhabitants locked inside to die or recover without spreading the disease further. Bodies pile up faster than they can be buried. The social fabric tears as people flee, as commerce stops, as ordinary life becomes impossible. In Woolsthorpe, Isaac is relatively safe. The hamlet is small, isolated, with little through traffic. The disease does not reach it, or if it does, only lightly. The manor house, which had been a place of confinement in his childhood, now becomes a refuge. He has the run of the house, access to the property, solitude. His mother and half-siblings are there, but they leave him alone, perhaps recognizing that he is engaged in some kind of work they don't understand, perhaps simply busy with their own concerns. Isaac sets up a workspace, probably in his room, fills it with books brought from Cambridge, papers, instruments he has made or acquired, and he begins to work. The first problem he tackles is motion. How do things move? What laws govern the motion of objects? Galileo has shown that falling bodies accelerate uniformly, that a ball rolling down an inclined plane picks up speed at a constant rate. Descartes has proposed that motion continues indefinitely unless something interferes with it. But no one has yet formulated precise, general laws that apply to all motion, that can predict exactly where an object will be at any future time given its starting position and velocity and the forces acting on it. This is a mathematical problem, but it's also more than that. It requires a new way of thinking about change, about how one quantity varies as another quantity varies, about instantaneous rates of change. Isaac invents what he calls the method of fluxines, which is his version of what will later be called calculus. The insight is this: to understand motion, you need to understand how position changes over time, which means you need to understand velocity. But velocity itself changes over time, which means you need to understand acceleration. And all of these involve rates of change, which can be thought of as the ratio of a small change in one quantity to the corresponding small change in another. But if you want the instantaneous rate, the exact speed at a precise moment, you need to let those small changes become infinitely small. This is a strange idea, philosophically troubling in some ways, because how can you divide by an infinitely small quantity? What does that even mean? Isaac pushes past the philosophical difficulties and focuses on making the method work. He develops notation, rules for manipulating these fluxines, techniques for solving problems. He can now, at least in principle, analyze any kind of changing quantity, any motion, any curve. He can find the slope of a tangent line to a curve at any point, which gives the instantaneous rate of change. He can find the area under a curve, which gives the total accumulation of some quantity. He discovers that these two operations, finding tangents and finding areas, are inverse operations, related through what will later be called the fundamental theorem of calculus. This is an extraordinary unification, a revelation that what seemed like separate problems are actually two sides of the same coin. He works through examples, fills pages with calculations, tests his method on various curves and motions. It works. He can solve problems that were previously unsolvable, can describe with precision the mathematics of change and motion. He does not publish any of this immediately, does not even write it up in a form intended for others to read. It's private work, notes for himself, a tool he is developing for his own use. But it's revolutionary, one of the most important mathematical advances in history, and he does it alone, in a manor house in the English countryside, while a plague ravages the nation. Simultaneously, he is thinking about light. What is light? How does it work? Why do prisms produce rainbows? The traditional view, going back to Aristotle and carried forward through medieval and Renaissance thought, is that white light is pure and simple, and that colors are produced by some kind of modification or darkening of that light. A prism, in this view, alters the light passing through it, adding something to create the spectrum of colors. But Isaac suspects this is wrong. He has a prism, a triangular piece of glass, and he begins experimenting with it in a darkened room. He lets a thin beam of sunlight enter through a small hole in the window shutter, pass through the prism, and project onto the opposite wall. What he sees is not just a spot of colored light but an elongated spectrum with red at one end, then orange, yellow, green, blue, and violet at the other end. This elongation is curious. If the prism were simply refracting or bending the light, the image should be circular, not stretched out. Isaac measures the length and width of the spectrum carefully and calculates what the dimensions should be if simple refraction were the only effect. The observed spectrum is too long. Something else is happening. He hypothesizes that white light is not simple but is actually a mixture of different colors, and that the prism is separating them, bending each color by a different amount. Red light is bent less than violet light, so they spread out into a spectrum. To test this, he designs more experiments. He takes the colored light from one prism and passes it through a second prism. If the colors are modifications of white light, the second prism should change them further. But they don't change. Red light remains red, blue light remains blue. The second prism refracts them, bends them further, but does not alter their color. This is strong evidence that colors are intrinsic properties of the light itself, not modifications imposed by the prism. He does another experiment even more ingenious. He uses a board with a small hole to isolate a single color from the spectrum produced by the first prism. He then directs that single color light through a second prism. Again, the color does not change. Only the direction and perhaps the intensity change. He tries recombining the separated colors, using a lens to bring them back together, and when all the colors of the spectrum are recombined, they produce white light again. This demonstrates that white light is composite, made up of all the colors, and that a prism does not create colors but merely separates what was already there. These experiments are conducted in near darkness, with beams of light moving through dusty air, projecting patterns on walls and boards. Isaac works methodically, setting up each test, observing carefully, recording results, thinking through what they mean. There is no one to discuss this with, no collaborator to suggest alternative interpretations or to confirm observations. It's just him and the light and the questions he is asking of it. He also thinks about how the eye sees color, how light interacts with matter, why the sky is blue, why objects have the colors they do. He concludes that objects appear colored because they reflect certain wavelengths of light and absorb others. A red apple is red because it reflects red light and absorbs the other colors. This is a mechanical explanation, replacing older ideas about colors being qualities or forms inherent in objects. Everything is starting to fit together into a coherent picture. Light is made of particles, or perhaps waves, traveling from source to eye, interacting with matter in predictable ways, carrying information about the world. While he is exploring light and developing calculus, he is also thinking about gravity. The story of the falling apple is famous, perhaps the most famous anecdote in the history of science, and like many famous anecdotes, it's difficult to separate fact from myth. The core story is that Isaac, sitting in the orchard at Woolsthorpe, sees an apple fall from a tree and begins to wonder why it falls. Why does it fall straight down toward the earth? Why doesn't it fly off sideways or upward? Is there some force pulling it? This is not, by itself, a revolutionary question. People have known for as long as people have existed that things fall. Aristotle explained it by saying that Earth, one of the four elements, has a natural tendency to move toward its natural place, which is the center of the cosmos. But Isaac has moved beyond Aristotle. He is thinking in terms of forces in motion, of mathematical descriptions. He wonders, if there is a force pulling the apple toward the earth, does that force extend beyond the surface of the earth? Does it reach the moon? The moon orbits the earth, moving in a roughly circular path. Something must be keeping it in that orbit, preventing it from flying off in a straight line, which is what objects do when no force acts on them, according to the principle of inertia that Galileo and Descartes have articulated. Could the same force that pulls the apple down also be pulling the moon, constantly deflecting it from a straight line and keeping it in orbit? Isaac does a calculation. He knows the radius of the Earth, more or less, from the measurements of earlier geographers. He knows the distance to the moon, which has been estimated using parallax measurements. He knows how long it takes the moon to orbit the Earth, about 27 days. From this, he can calculate how fast the moon is moving and how much it falls toward the Earth each second, meaning how much its path curves inward compared to a straight line. Then he can ask, if the force of gravity extends to the moon and follows an inverse square law, meaning it gets weaker with the square of the distance, would the acceleration of the moon toward the Earth match the acceleration of a falling apple? He does the calculation. The numbers are rough because the exact radius of the Earth is uncertain and there are approximations involved. The result is close but not exact. Close enough to suggest that the idea might be right, that there might be a single force governing both the fall of an apple and the orbit of the moon, but not close enough to be certain. Isaac notes the calculation, recognizes its promise, but does not pursue it to completion at this time. There are other problems to work on, other questions to answer. 18 months pass in this way. The plague subsides in late 1666, and by the spring of 1667, Cambridge reopens. Isaac returns to the university, carrying with him notebooks filled with discoveries that no one else knows about, insights that will not be published for years, ideas that will reshape physics and mathematics. But in the spring of 1667, he is still an unknown recent graduate, resuming his studies, working toward becoming a fellow of the college. Returning to Cambridge after the intense solitude and productivity of Woolsthorpe must be a strange experience. Isaac has, in a sense, moved far beyond the level of his teachers. He has developed a mathematical method that is more powerful than anything they teach. He has conducted optical experiments that overturn the standard theory of color. He has glimpsed a theory of gravity that could unify earthly and celestial mechanics. But he does not announce any of this. He does not stride into the college and declare that he has revolutionized natural philosophy. Instead, he quietly resumes his place, fulfills his academic obligations, and continues his private work. In 1667, Isaac is elected a Fellow of Trinity College, which provides him with a stipend, rooms, and the security to continue his studies. It's a position of modest prestige, given to promising scholars, and it comes with certain requirements, including eventually taking holy orders in the Church of England. Isaac accepts the fellowship and settles into college life, though he remains largely solitary, focused on his work rather than on social or political affairs within the university. He continues experimenting with light, refining his understanding, building better equipment. Telescopes are the great scientific instrument of the age, allowing astronomers to observe the moons of Jupiter, the phases of Venus, the mountains on the moon, the rings of Saturn. But telescopes of the time use lenses to gather and focus light, and lenses have a problem: chromatic aberration. Because different colors of light refract by different amounts, a lens cannot focus all colors to the same point. The result is a blurry, color-fringed image. Isaac, now understanding that white light is composite, realizes that this is an inherent problem with refracting telescopes. You cannot fix it by making better lenses because the problem is fundamental to how lenses work with composite light. But there is an alternative: reflecting telescopes which use mirrors instead of lenses. Mirrors do not separate colors. They reflect all wavelengths equally. Isaac designs and builds a small reflecting telescope, only about 6 inches long, using a curved mirror to gather light and a flat mirror to direct it to an eyepiece. It's a difficult technical challenge. The mirror must be precisely shaped and polished to a smooth, reflective finish. Isaac grinds and polishes the mirror himself, using metal, achieving a surface quality good enough to produce clear images. The resulting telescope is small but effective, magnifying objects about 40 times and producing clearer images than much larger refracting telescopes. This telescope attracts attention. It's a novel design and it works. Isaac demonstrates it to colleagues at Cambridge and word spreads. In 1671, the telescope is shown to the Royal Society in London, the premier scientific organization in England. The members of the society are impressed. This is a significant practical achievement, a new kind of instrument that avoids the limitations of refractors. Isaac is elected a Fellow of the Royal Society in 1672, at the age of 29, gaining recognition and entry into the community of natural philosophers. Encouraged by this reception, Isaac decides to share some of his work on light. In February 1672, he sends a letter to the Royal Society describing his experiments with prisms and his conclusions about the nature of white light and colors. The letter is read at a society meeting and then published in the Society's journal, Philosophical Transactions. It's Isaac's first major publication, his first public presentation of his ideas. The response is not what he hopes for. While some readers are impressed, others are skeptical or critical. Robert Hooke, one of the leading figures in the Royal Society, a skilled experimenter and a brilliant but contentious personality, raises objections. Hooke has his own theories about light, and he does not accept Isaac's conclusions. He suggests alternative explanations for the experiments, argues that Isaac's interpretation is not the only possible one, and generally treats the work as interesting but not definitive. Isaac is stung by this criticism. He has spent years on this work, conducted careful experiments, thought through the implications. He is certain that his conclusions are correct. To have them questioned, to have someone like Hooke suggest that he might be wrong, is deeply upsetting. He responds with a long, detailed letter defending his position, explaining his experiments more fully, pointing out the flaws in Hooke's objections. But Hooke is not convinced, and other critics join in. There is a back and forth of letters published in the journal, a public dispute that drags on for months. Isaac finds this process excruciating. He does not enjoy debate, does not like having his work picked apart and questioned, especially by people he does not believe understand it properly. The experience leaves him bitter and wary. In later letters, he complains about the time wasted in responding to critics, about the vexation of public controversy. He begins to regret publishing at all, starts to feel that sharing his work brings more trouble than it's worth. This pattern will repeat throughout his career. Isaac makes a discovery, eventually shares it, faces criticism or disputes, reacts badly, and withdraws further into privacy. It's a cycle driven by his personality, his sensitivity to criticism, his difficulty with personal conflict. He is capable of fierce intellectual combat when he believes he is right, but he takes attacks on his ideas as personal attacks, and he does not forgive or forget. Through the 1670s, Isaac continues working mostly in private. He conducts more optical experiments, refines his mathematical methods, explores other areas of natural philosophy. He also begins serious work in alchemy, setting up a laboratory with furnaces and equipment, conducting experiments, filling notebooks with observations and speculations. Alchemy is, in this period, a strange hybrid of chemistry, mysticism, and philosophy. It is concerned with the transformation of substances, particularly the transmutation of base metals into gold, but it is also a spiritual practice, a search for hidden knowledge, a way of engaging with nature's deepest secrets. Isaac takes it seriously. He reads widely in alchemical literature, both contemporary and ancient, studying the cryptic texts, trying to decode the symbolic language. He conducts experiments, heating various substances, mixing them, observing the results, looking for patterns and transformations. He is meticulous, recording everything, but he is also secretive. Alchemy is not quite respectable, not quite acceptable in the way that mathematics or astronomy or even optics is. It is associated with charlatans and deceivers, with impossible promises. Isaac does not publish his alchemical work, does not discuss it openly. It remains a private obsession, pursued in the hours when he is not engaged in more public scientific work. What drives him to alchemy? Perhaps the same thing that drives him to physics and mathematics. The desire to understand, to uncover the fundamental principles governing nature. Alchemists believe that all substances are composed of a single primal matter, which can be transformed from one form to another if you know the right processes. This is not completely unreasonable. It's a search for the underlying unity of matter, which is not so different from searching for the underlying laws of motion or the composition of light. Of course, the specific goal of turning lead into gold is impossible, and many of the alchemical theories are wrong. But the impulse, the drive to dig deeper into the nature of matter, is legitimate, and some of the experimental techniques and observations from alchemy will feed into the development of chemistry. Isaac spends long hours in his laboratory, breathing the fumes of heated metals and chemicals, exposing himself to mercury and other toxic substances. Mercury poisoning can cause a range of symptoms. tremors, irritability, insomnia, memory problems, mood swings. There is some evidence from analysis of locks of Isaac's hair that survived that he had elevated levels of mercury in his system. Whether this affected him significantly is debated, but it's possible that his alchemical work had a physical cost. He is also working on theology, another private obsession. Isaac is deeply religious, but his religion is not orthodox. He reads the Bible in the original languages, studies early church history, works through complex textual and doctrinal questions. And he comes to a conclusion that is, in the context of 17th century England, dangerous. He rejects the doctrine of the Trinity. The Trinity, the idea that God exists as three persons, Father, Son, and Holy Spirit, in one divine being, is a cornerstone of Christian orthodoxy, affirmed by the major creeds and defended by the Church. To deny it is heresy. Isaac concludes, based on his reading of Scripture and history, that the Trinity is a later invention, a corruption of the original Christian message. He becomes an Arian, believing that Jesus is divine but subordinate to God the Father, not co-equal and co-eternal. This is a profound and sincere conviction, not a casual or strategic position. But it's also a conviction he must keep secret. As a fellow of Trinity College, he is required to take holy orders, to become an ordained minister in the Church of England. But he cannot, in good conscience, take orders in a church whose fundamental doctrine he believes is false. This puts him in a difficult position. If he does not take orders, he will lose his fellowship. If he reveals his true beliefs, he will be expelled and possibly prosecuted. He delays, finds excuses, hopes for some resolution. Eventually, in 1675, he receives a special dispensation from the king, exempting holders of the Lucasian professorship, a position Isaac now holds, from the requirement to take holy orders. This saves his career, but it does not resolve the inner conflict between his public role in an Anglican institution and his private heretical beliefs. The Lucasian professorship, which Isaac was appointed to in 1669 at the age of just 26, is a prestigious position, endowed to support a professor of mathematics at Cambridge. Isaac's predecessor, Isaac Barrow, recognized Newton's superior abilities and stepped aside to allow the younger man to take the chair. As Lucasian professor, Isaac is required to give lectures, and he does, though often to empty rooms or nearly empty rooms. His lectures on optics and mathematics are detailed and technical, not designed to entertain or to reach a broad audience. Students find them difficult or incomprehensible. Isaac does not seem to care much whether anyone attends or understands. He is fulfilling the requirement, but his heart is in his private research, not in teaching. By the early 1680s, Isaac Newton is known in a small circle as a brilliant mathematician and natural philosopher, the inventor of a reflecting telescope, the author of controversial theories about light. But he has published little, most of his work remains in manuscript form, and his reputation, while solid, is not extraordinary. He is one figure among several in the English scientific community, talented and difficult, a fellow of the Royal Society who rarely attends meetings, a professor who does not much like teaching. He could easily have remained at this level, contributing to knowledge but not transforming it. What changes everything is a visit from Edmund Halley in August 1684. Halley is a younger astronomer, energetic and sociable, a fellow of the Royal Society, interested in the problem of planetary motion. The planets move in elliptical orbits around the Sun, as Johannes Kepler had determined empirically decades earlier from careful analysis of observations. But why? What force produces those elliptical orbits? Several people, including Hooke and Christopher Wren, have speculated that there might be an inverse square law of attraction between the Sun and the planets, meaning the force decreases with the square of the distance. But no one has been able to prove that an inverse square law produces elliptical orbits. Halley travels to Cambridge to ask Isaac about this problem. When he poses the question, what kind of orbit would result from an inverse square force? Isaac immediately answers, an ellipse. Halley is astonished. He asks how Isaac knows this. Isaac replies that he has calculated it. Halley asks to see the calculation. Isaac looks through his papers but cannot find it immediately. He promises to send it to Halley later. After Halley leaves, Isaac reconstructs the calculation, and in November, he sends Halley a short treatise titled De Motu Corporum in Gyrum, or On the Motion of Bodies in Orbit. It contains the proof that an inverse square law of attraction produces elliptical orbits, along with other results about motion and gravity. Halley reads it and immediately recognizes that this is something extraordinary. He urges Isaac to expand the work, to develop it into a full treatment of mechanics and astronomy. Isaac, perhaps sensing that he has finally found the key to a problem that has puzzled him for years, perhaps encouraged by Halley's enthusiasm, agrees. He begins writing in earnest. For the next 18 months, from late 1684 through early 1687, Isaac works with intense concentration, often forgetting to eat or sleep, rarely leaving his rooms, consumed by the project. He is writing the Principia, the Philosophiae Naturalis Principia Mathematica, or Mathematical Principles of Natural Philosophy. It will be his masterpiece, the work that establishes him as the greatest scientist of his age and one of the greatest of any age. The Principia is structured in 3 books. The first book lays out the fundamental principles of mechanics, the 3 laws of motion and the law of universal gravitation. The second book deals with motion in resisting media, such as fluids. The third book applies the principles to the system of the world, explaining the motions of planets, moons, comets, and the tides. The whole thing is written in Latin, using the geometric style of classical mathematics with propositions, proofs, lemmas, corollaries. It is rigorous, dense, difficult. Isaac writes it that way deliberately, in part because geometric proofs are considered more certain than algebraic manipulations, in part because he wants to limit his audience to serious readers who will not misunderstand or misuse the ideas. The 3 laws of motion are deceptively simple. The first law states that an object remains at rest or in uniform motion in a straight line unless acted upon by a force. This is a refinement of the principle of inertia, making it clear that no force is needed to maintain motion, only to change it. The second law states that the change in motion is proportional to the force applied and occurs in the direction of that force. In modern notation, this is written as F equals m times a, force equals mass times acceleration. The third law states that for every action there is an equal and opposite reaction, meaning that forces come in pairs, each body exerting a force on the other. These laws describe how objects move in response to forces, but they do not, by themselves, tell you what forces exist. For that, Isaac introduces the law of universal gravitation. Every particle of matter attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This is a stunning claim. It says that gravity is not just something that happens on Earth, not just something that pulls apples down or keeps us on the ground, but a universal force acting between all masses everywhere. The same force that pulls the apple pulls the moon, holds the planets in their orbits, governs the motion of comets, causes the tides. With these laws, Isaac can explain and predict an enormous range of phenomena. He derives Kepler's laws of planetary motion from the law of gravitation, showing that elliptical orbits are a natural consequence of an inverse square force. He explains why planets move faster when they are closer to the sun and slower when they are farther away. He calculates the shape of the Earth, showing that it should be slightly flattened at the poles due to its rotation. He explains the precession of the equinoxes, the slow wobble in the Earth's axis. He analyzes the orbits of Jupiter's moons, the path of comets, the timing and height of ocean tides. Problem after problem that had resisted explanation now yields to his mathematical framework. The work is exhausting. Isaac pushes himself to the limit, driven by the vision of a complete system, a unified theory of motion and gravitation that explains the mechanics of the heavens and the earth. He argues with himself, refines proofs, checks calculations, worries about loose ends and potential objections. Halley visits periodically to check on progress and to encourage him, sensing that something of immense importance is being created. But Halley also has to navigate Isaac's temperament, his insecurities, his tendency to take offense. One significant crisis arises from Robert Hooke. Hooke hears that Isaac is working on a major treatise and writes to claim that he, Hooke, deserves credit for the idea of the inverse square law. Hooke had indeed suggested this idea in correspondence and in publications, though without proof or detailed development. Isaac is furious. He believes, with justification, that his work goes far beyond Hooke's speculations, that he has done all the real work of proving and applying the law, and that Hooke is trying to steal credit. Isaac threatens to suppress the third book of the Principia, the part dealing with the system of the world, rather than give Hooke any satisfaction. Halley manages to calm him down, pointing out that withholding the book would only harm Isaac's own reputation and that the work speaks for itself. Isaac agrees to proceed but makes sure that any reference to hook in the text is minimal and grudging. In the summer of 1687, the Principia is finally published. Halley oversees the publication, even paying the printing costs out of his own pocket because the Royal Society's finances are shaky. The book appears in Latin in a small print run, expensive, aimed at a scholarly audience. It is not an immediate popular success, because it is simply too difficult for most people to read. But among those capable of understanding it, the impact is immediate and profound. Here, finally, is a system that explains the universe. Not just describes it, not just catalogs the motions of planets and stars, but explains why they move as they do, predicts where they will be in the future, reduces the complexity of the heavens to a few simple, universal laws. The universe operates like a machine, governed by mathematical principles, and Isaac Newton has discovered those principles. It is the culmination of the scientific revolution, the moment when the new mechanical philosophy proves itself capable of accounting for the most difficult and important phenomena in nature. Not everyone accepts it immediately. Descartes followers, particularly on the continent, are wedded to a different system, one that explains planetary motion through vortices of circulating matter rather than through action at a distance. Isaac's idea that the sun and planets exert forces on each other across empty space, without any physical contact, strikes some as mystical or occult, a return to the kind of hidden qualities that the new philosophy was supposed to banish. Isaac himself is not entirely comfortable with action at a distance. He says in the Principia that he is not proposing a cause for gravity, only describing how it behaves mathematically. But the mathematics works so well, explains so much, that gradually over the following decades the Newtonian system is accepted. It becomes the foundation of physics, the framework within which scientists work for the next 2 centuries. For Isaac, the publication of the Principia represents a kind of culmination. He is 44 years old. He has finally shared his greatest work with the world. The response, among those who matter, is recognition of his genius. He is no longer just one natural philosopher among many. He is the preeminent figure, the man who has explained the system of the world. But this recognition does not bring him peace or satisfaction. If anything, it brings new pressures, new disputes, new demands on his time. The years following the publication of the Principia are difficult. Isaac is exhausted from the intense effort of writing the book. He has health problems, possibly related to his exposure to mercury and other chemicals during his alchemical work, possibly just the result of stress and overwork. He is irritable, quick to anger, defensive about his work. The joy of discovery, if he ever experienced it as joy, has given way to something darker. A sense of having given so much and received so little in return, of being misunderstood and unappreciated, of being engaged in endless, draining conflicts with people who do not understand what he has accomplished. In 1693, Isaac suffers what appears to be a mental breakdown. He writes strange, paranoid letters to friends, accusing them of plotting against him or wishing him ill. He complains of insomnia, of inability to eat or think clearly. He withdraws from correspondence, from work, from social contact. For several months he seems lost, unstable, unlike himself. Friends who receive these letters are worried and confused. Gradually, over the course of the year, Isaac recovers. He apologizes for the letters, explains that he was ill, resumes more normal behavior. But the episode is a sign of the toll that years of solitary, obsessive work, combined with public disputes and personal isolation, have taken on him. After this crisis, Isaac turns away from intense scientific work. He does not produce anything comparable to the Principia after this point. Instead, he moves toward a different phase of his life, one more engaged with the public world, with institutions and politics and practical affairs. In 1696, he is appointed Warden of the Royal Mint, responsible for overseeing the production of England's coinage. This is a significant government position, well paid, and it requires him to move to London permanently. He accepts the appointment, perhaps seeking a change, perhaps attracted by the salary and status, perhaps simply needing to do something different after the exhaustion of his creative years. As warden, and later as master of the mint, Isaac proves to be efficient and effective. England is in the midst of a currency crisis, with much of the silver coinage clipped or counterfeited, undermining the economy. A great recoinage is undertaken, calling in the old, damaged coins and minting new ones. Isaac oversees this massive operation, managing the work of the mint, dealing with technical problems, coordinating with government officials. He also takes an active role in prosecuting counterfeiters, interviewing suspects, gathering evidence, even personally conducting interrogations. Counterfeiting is a capital crime, and Isaac shows no mercy, sending several people to the gallows. It's a side of him that seems at odds with the image of the detached, abstract thinker. Here is Newton as government enforcer, using his analytical skills to hunt down criminals, displaying a ruthlessness that suggests how seriously he takes the responsibilities of his office. In 1699, he is promoted to Master of the Mint, a position he holds for the rest of his life. The job makes him wealthy and socially prominent. He maintains a household in London, entertains guests, participates in the life of the city. But he is never comfortable in social settings, never at ease with small talk or the rituals of polite society. He remains awkward, stiff, more interested in ideas than in people. In 1703, Isaac is elected president of the Royal Society, a position he will hold until his death. As president, he wields considerable influence over the direction of science in England. He attends meetings, oversees the society's affairs, uses the position to promote his views and to settle old scores. He is not a generous or democratic leader. He dominates the society, suppresses opposition, ensures that those who disagree with him are marginalized. The Royal Society, under his presidency, is less a community of equals and more an extension of his personal authority. One of the most bitter and destructive conflicts of his later years is the priority dispute over calculus with Gottfried Wilhelm Leibniz. Leibniz, a German philosopher and mathematician, independently developed calculus in the 1670s, using a different notation and approach than Isaac's method of flux science. Leibniz published his work in the 1680s, making it widely available and influential, particularly on the continent. Isaac, who had developed his method earlier but had not published it, begins to suspect that Leibniz stole his ideas. There is no evidence that Leibniz had access to Isaac's unpublished manuscripts, and the historical consensus is that the two men developed calculus independently. But Isaac cannot accept this. He believes that the priority belongs to him, that he was first, and that Leibniz is either a thief or, at best, a secondary figure who does not deserve equal credit. The dispute escalates in the 17th lens. Letters are exchanged, accusations made, supporters on both sides weigh in. Isaac uses his position as president of the Royal Society to orchestrate an investigation into the matter. The Society appoints a committee which, not surprisingly given that Isaac controls it, concludes that Isaac was the first inventor and that Leibniz plagiarized his work. The committee's report is published, and Isaac even writes parts of it himself, anonymously, presenting what is supposed to be an impartial judgment but is actually his own self-serving account. Leibniz, in Germany, fights back, defending his honor, insisting on his independence. The dispute becomes nationalistic, with English scientists supporting Isaac and continental scientists supporting Leibniz. It's ugly, petty, and ultimately pointless. Both men made fundamental contributions, both deserve credit, and the world would have been better served by cooperation and mutual recognition. But Isaac cannot let it go. He pursues the dispute long after it serves any purpose, driven by pride and a deep-seated need to be acknowledged as superior. Leibniz dies in 1716, still under attack, his reputation damaged in England though secure elsewhere. Isaac outlives him by more than a decade, never relenting, never acknowledging any fault or generosity toward his rival. It is one of the uglier chapters in the history of science, a reminder that even great minds can be petty, vindictive, and obsessed with status. In his final years, Isaac continues to work, though not on new science. He prepares new editions of the Principia, revising and expanding the text, adding new material, responding to criticisms. He works on a chronology of ancient kingdoms, trying to reconcile biblical history with secular sources, a project that reflects his ongoing interest in theology and history. He continues his theological studies, writing manuscripts that argue against the Trinity and explore biblical prophecy, though he never publishes any of this material, knowing it would be dangerous. He is old now, in his 70s, the last survivor of the generation that launched the scientific revolution. Galileo died the year Isaac was born, creating a kind of symbolic passing of the torch. Descartes, Huygens, Hooke, Leibniz, all the great figures he contended with or learned from, are gone. Isaac remains, an institution unto himself, the acknowledged master of natural philosophy, revered, feared, but not, perhaps, loved. He dies on March 20th, 1727, at the age of 84. In his last days he suffers from severe pain, possibly from kidney stones, and declines medical interventions that might prolong his suffering. He dies at home in London, attended by friends and relatives but in some essential sense alone, as he has been for most of his life. His death is treated as a national event. He is given a state funeral, a rare honor for someone who is not nobility or a high government official. His body lies in state, and then he is buried in Westminster Abbey, among the kings and heroes of England. The monument erected over his tomb shows him reclining with allegorical figures and symbols of his achievements. A prism, a telescope, coins from the mint, a representation of the solar system. The inscription praises him in grandiose terms. Let mortals rejoice that there has existed such and so great an ornament to the human race. It's fitting in a way, though Isaac himself might have found it uncomfortable. He was never comfortable with praise or with the public gaze, always preferring the privacy of his own thoughts to the attention of the world. What Isaac Newton left behind is difficult to overstate. The Principia became the foundation of physics for 2 centuries. His laws of motion and gravitation explain not just the orbits of planets but the behavior of all moving objects, from cannonballs to comets. Engineers used his principles to design machines, predict trajectories, understand forces. Astronomers used his laws to discover new planets, calculate orbits, understand the structure of the solar system and the motions of stars. The success of Newtonian mechanics was so complete, so overwhelming, that it seemed for a long time that he had solved physics, that all that remained was to work out details and apply the principles to new problems. Of course, that turned out not to be true. In the early 20th century, Einstein's theory of relativity showed that Newton's laws are approximations that work well at everyday speeds and scales but break down at very high speeds or in very strong gravitational fields. Quantum mechanics revealed a different set of laws governing the behavior of atoms and subatomic particles. Newton's universe, deterministic and mechanical, was replaced by something stranger and more complex. But this does not diminish Newton's achievement. His laws are still used for almost all practical purposes, from launching spacecraft to building bridges. They remain the correct description of motion in the regime where we live, and the fact that there are deeper or more general theories does not erase the fact that Newton discovered a profound truth about how nature works. His work on light also had a lasting impact. His experiments with prisms demonstrated that white light is composite, a mixture of colors, and laid the groundwork for the science of spectroscopy, which would eventually allow scientists to determine the composition of stars and distant objects by analyzing their light. His reflecting telescope design is still used in refined form in many of the world's most powerful telescopes. His willingness to conduct careful, systematic experiments and to draw conclusions based on evidence rather than authority set a standard for how science should be done. But perhaps his greatest legacy is more abstract. The idea that nature is governed by mathematical laws, that these laws are universal and discoverable, and that human reason, rigorously applied, can uncover them. Before Newton, there were pieces of this idea, scattered insights, partial theories. After Newton, it became the foundation of the scientific worldview. The universe is not capricious or mysterious. It follows rules. Those rules can be written down in equations. And those equations allow us to predict, to control, to understand. This is the vision that has powered science and technology for the past 3 centuries, the belief that has driven exploration and discovery and progress. It begins in its modern form with Isaac Newton. He was, by all accounts, a difficult person. Isolated, defensive, secretive, vindictive, unable to forgive or forget slights, capable of extraordinary pettiness in disputes, obsessed with priority and recognition. He formed no close relationships, left no emotional legacy of warmth or generosity. His religious views, which he kept hidden, suggest a mind that questioned orthodoxy but could not share those questions, that valued truth but feared the consequences of speaking it. His pursuit of alchemy, consuming years of effort, led nowhere, or at least nowhere that he acknowledged. His later years, spent in administrative roles and bitter disputes, seem a decline from the heights of his creative period. And yet, in those creative years, particularly in the months at Woolsthorpe during the plague and the intense period of writing the Principia, he achieved something that perhaps no one else could have achieved. He saw patterns where others saw only complexity. He found the mathematical language to describe motion and force and gravity. He connected the fall of an apple to the orbit of the moon, the motion of planets to the ebb and flow of tides, the light of the sun to the colors of the rainbow. He took the chaos of sensory experience and found order within it, wrote down the rules, showed that the universe is comprehensible. There is a famous line attributed to Isaac, though he was actually paraphrasing an earlier writer, Bernard of Chartres. "If I have seen further, it is by standing on the shoulders of giants." He wrote this in a letter to Hooke, and it's often quoted as an expression of humility, an acknowledgement of his debt to predecessors. But the letter was written in the context of a dispute, and some scholars think the line was actually a veiled insult, a reference to Hooke's short stature and his relatively minor contributions. Whether generous or cutting, the phrase captures a truth. All knowledge builds on what came before. Isaac absorbed the work of Galileo, Kepler, Descartes, and many others. He synthesized their insights, corrected their errors, and went beyond them. But when we think of Isaac Newton, we do not primarily think of synthesis or incremental progress. We think of breakthroughs, of fundamental discoveries, of a mind that saw deeper and further than anyone else. He was not just standing on the shoulders of giants. He was, himself, a giant, the figure on whose shoulders later scientists would stand. Einstein studied Newton, learned from him, and eventually found the places where Newton's theories break down. But Einstein revered Newton, recognized him as a predecessor of unparalleled insight. And that reverence is shared by every physicist since, every scientist who works in the tradition that Newton helped to establish. The universe that Isaac Newton revealed is, in some ways, a cold and mechanical one. There is no room in Newtonian mechanics for purpose or intention, no sense that the planets move because they choose to or because they are fulfilling some cosmic role. They move because they are pulled by gravity, because the force of attraction between them and the sun deflects them from a straight line, and the mathematics of that deflection produces elliptical orbits. This is explanation without meaning, description without values. It tells us how but not why, at least not in any deeper, purposeful sense. For Isaac himself, this was not a problem. He believed that God created the universe and set it in motion according to these laws. The laws were divine, expressions of God's will and rationality, and discovering them was a way of understanding God's creation. But for others, the Newtonian worldview could feel disenchanting, could seem to drain the universe of magic and mystery, replacing it with equations and forces. The poet John Keats would later write of how Newton destroyed the poetry of the rainbow by reducing it to the refraction of light through prisms. This complaint mistakes the nature of understanding. Knowing how something works does not make it less beautiful, less wonderful. If anything, the more you understand the complexity and elegance of the natural world, the more reason there is for awe. Isaac Newton spent 84 years on this earth, and in that time he changed humanity's understanding of the cosmos more than almost anyone before or since. He began life as a premature, fatherless infant who should not have survived. He endured abandonment, loneliness, poverty, social awkwardness, illness, and conflict. He worked in isolation, driven by something he could not fully articulate, a hunger to understand that consumed his energy and shaped his life. He gave the world a new way of seeing, a new set of tools for understanding, a vision of a rational, ordered universe governed by mathematical laws. And at the end, he is remembered, mourned, buried with honor. But the man himself, the child alone in the orchard, the young scholar working by candlelight, the obsessive experimenter in his darkened room, the fierce defender of his priority, remains elusive, hidden behind the work, behind the monument, behind the equations that bear his name. We know what he discovered, but we can only guess at what it felt like to discover it, what it cost him, what he gained and lost in the pursuit. The stars continued to move in their orbits, following the laws he described, indifferent to human concerns, beautiful and remote and comprehensible because of the work of one difficult, brilliant, solitary man who was born in a stone house in Lincolnshire on a cold Christmas day and who, against all odds, survived to explain the universe. The legacy that Isaac Newton left behind extended far beyond the pages of the Principia or the glass prisms in his laboratory. It was a legacy that transformed not just science but the entire intellectual landscape of the centuries that followed. The Enlightenment, that great flowering of reason and progress in the 18th century, drew much of its confidence from Newton's example. Here was proof that human minds, using observation and mathematics, could penetrate the deepest mysteries of nature. If Newton could explain the movements of planets and the nature of light, What else might be possible? Voltaire, the French philosopher and satirist, became one of Newton's most enthusiastic continental champions. He spent time in England in the 1720s and was impressed by the intellectual freedom and scientific sophistication he found there. He attended Newton's funeral and was struck by the honors paid to a man of learning. In France, by contrast, scientists and philosophers often struggled for recognition and respect. Voltaire returned to France determined to spread Newtonian ideas. He wrote a popularization of Newton's physics, explained the theory of gravitation to French readers, contrasted Newton's experimental approach favorably with the speculative systems of Descartes. Through Voltaire and others, Newtonian mechanics became the symbol of a new kind of thinking. Empirical, mathematical, freed from ancient authorities and religious dogma. The impact on philosophy was equally profound. If the universe operates according to fixed mathematical laws, what does that mean for human beings? Are we also machines governed by deterministic laws? Do we have free will, or are our actions as predetermined as the orbit of Mars? These questions occupied philosophers throughout the 18th and 19th centuries. Some embraced a materialistic worldview, arguing that everything, including consciousness and choice, can ultimately be explained in terms of matter and motion. Others tried to carve out space for human agency and moral responsibility within a Newtonian universe. The success of Newtonian mechanics also raised expectations about what science could achieve. If physics could be reduced to a few elegant laws, perhaps other domains could be similarly systematized. Economists tried to find the laws governing markets and trade. Political theorists searched for the principles of good governance. Even moralists hoped to discover universal ethical laws analogous to the laws of motion. This faith in systematic, rational understanding sometimes led to genuine insights and sometimes to naive overreach, but it reflected the profound influence of Newton's example. In practical terms, Newtonian mechanics became the foundation for engineering and technology. The Industrial Revolution, which transformed human society in the 18th and 19th centuries, depended on understanding forces, motion, energy, and machines. Engines, factories, railways, bridges, ships. All of these were designed using principles that Newton had articulated. His laws allowed engineers to calculate stresses and strains, predict how structures would respond to loads, optimize the efficiency of machines. The modern world, built on steam power and then electricity and then internal combustion, could not have developed without the theoretical framework that Newton provided. Astronomy, too, entered a golden age powered by Newtonian mechanics. Astronomers used his laws to predict the return of comets, calculate the masses of planets from the orbits of their moons, discover new planets through the wobbles they induced in known ones. In 1781, William Herschel discovered Uranus, the first new planet found since antiquity. By the early 19th century, astronomers noticed that Uranus was not following the predicted path. Its orbit showed small deviations that could not be accounted for by the gravitational influence of the known planets. Two mathematicians, John Couch-Adams in England and Urbain Le Verrier in France, independently used Newton's laws to calculate where an unknown planet would have to be to produce the observed deviations. In 1846, astronomers pointed their telescopes to the predicted location and found Neptune. It was a stunning confirmation of the power of Newtonian mechanics, an entire planet, invisible to the naked eye, discovered not by observation but by mathematics. This success was not just a technical achievement but a philosophical statement. It demonstrated that the universe is knowable, that hidden truths can be uncovered through reason and calculation, that nature really does follow mathematical laws and that humans can master those laws. The discovery of Neptune represented the high water mark of confidence in the Newtonian worldview, a moment when it seemed that all of nature's secrets would eventually yield to patient, careful analysis. Yet even at this moment of triumph, there were hints that Newton's system was not the final word. The planet Mercury, closest to the Sun, showed a small but persistent anomaly in its orbit. The point at which Mercury comes closest to the Sun, the perihelion, slowly advances over time, tracing out a rosette pattern rather than a perfect ellipse. Most of this precession could be explained by the gravitational influence of other planets, but a tiny residual remained. 43 seconds of arc per century, a minuscule discrepancy, but one that bothered astronomers because Newtonian mechanics offered no explanation for it. Various hypotheses were proposed. Perhaps there was another planet even closer to the Sun, or perhaps the Sun was slightly non-spherical, or perhaps there was some subtle effect that had been overlooked. But none of these explanations worked. The anomaly remained. In the meantime, other cracks were appearing in the edifice of classical physics. Experiments with electricity and magnetism, particularly the work of Michael Faraday and James Clerk Maxwell in the 19th century, revealed phenomena that did not fit neatly into the Newtonian framework. Maxwell showed that light is an electromagnetic wave traveling at a fixed speed through space. But Newton's mechanics included no such restriction. In Newtonian physics, you can always go faster by adding more velocity. If light travels at a certain speed relative to what, exactly? What is the medium through which it propagates? Physicists hypothesized an ether, an invisible substance filling all of space, through which light waves travel. But experiments failed to detect this ether, and by the end of the 19th century, it was clear that something was wrong, though no one quite knew what. In 1905, Albert Einstein published his theory of special relativity, which resolved the problem by asserting that the speed of light is the same for all observers, regardless of their motion, and that space and time are not absolute but relative, intertwined in a four-dimensional structure called spacetime. This required abandoning some of Newton's most fundamental assumptions. In Newtonian mechanics, time is universal and absolute, ticking away at the same rate everywhere. In Einstein's relativity, time is flexible, passing at different rates for observers moving at different speeds or experiencing different gravitational fields. The old concepts of absolute space and absolute time, which Newton had taken as foundational, turned out to be approximations that work well at low speeds but break down as you approach the speed of light. 10 years later, Einstein extended his theory to include gravity. In his general theory of relativity, gravity is not a force acting at a distance as Newton had described it, but a curvature of spacetime caused by mass and energy. Massive objects like stars and planets bend the fabric of spacetime around them, and other objects move along curved paths in this bent spacetime. This is what we perceive as gravitational attraction. The equations of general relativity reduced to Newton's law of gravitation in the limit of weak gravitational fields and low speeds, meaning Newton's laws are still correct for most practical purposes. But in extreme conditions, near black holes or in the early universe or in the orbit of Mercury close to the Sun, general relativity gives different, more accurate predictions. And indeed, Einstein's theory immediately explained the anomalous precession of Mercury's orbit. The curvature of spacetime near the Sun is strong enough to produce a small additional effect beyond what Newton's laws predict, exactly accounting for the observed 43 seconds of arc per century. It was one of the first confirmations of general relativity, a sign that Einstein had found a deeper truth about gravity than Newton had. Another confirmation came in 1919, when astronomers observed that starlight passing near the Sun during a solar eclipse was bent by a precise amount that general relativity predicted. Einstein became world-famous overnight, and Newtonian mechanics, while still enormously useful, was dethroned from its position as the ultimate truth about the universe. But this dethronement does not diminish Newton. Science progresses by building on and occasionally overturning previous theories. Newton himself had built on and corrected Aristotle, Ptolemy, and others. Einstein built on and corrected Newton. And someday someone may build on and correct Einstein. This is how knowledge advances. Each generation sees further by standing on the shoulders of the previous one, to use Newton's own metaphor. And Newton's shoulders were high enough to support 2 centuries of scientific progress. Moreover, for almost all practical purposes, Newton's laws are still the right ones to use. Engineers designing buildings, physicists calculating trajectories, astronomers studying planetary systems. Almost everyone, almost all the time, uses Newtonian mechanics because it is simpler and more than accurate enough for the task at hand. Einstein's corrections only matter in extreme conditions. In the world of everyday experience, the world of falling apples and orbiting moons and spinning planets, Newton's laws describe reality with extraordinary precision. The same is true of quantum mechanics, the other great revolution of early 20th century physics. At the scale of atoms and subatomic particles, matter behaves in ways that are completely incompatible with Newtonian mechanics. Particles exist in superpositions of states, have properties that are fundamentally uncertain, exhibit wave-particle duality, and are connected by non-local correlations that Einstein himself found disturbing. But again, these quantum effects average out at larger scales, and the classical Newtonian picture emerges as an excellent approximation for objects larger than molecules. So Newton's laws continue to work where they always worked, in the realm of tangible objects moving at tangible speeds. What Newton gave us, then, is not the final truth about the universe but something perhaps more valuable. A framework that is profoundly correct within its domain of applicability, that allows precise predictions and practical applications, and that served as the foundation for centuries of scientific progress. He showed that nature is lawful, that those laws can be expressed mathematically, and that human reason can discover them. These insights remain true even if the specific laws he proposed have been refined or superseded in certain regimes. His work on light and optics has also endured and evolved. The understanding that white light is composite, that it can be separated into a spectrum of colors, became the basis for spectroscopy. In the 19th century, scientists discovered that when elements are heated, they emit light at specific wavelengths, producing characteristic patterns of bright lines in a spectrum. By analyzing these spectral lines, chemists could identify which elements were present in a substance. Astronomers realized they could apply the same technique to stars, analyzing the spectrum of starlight to determine what the star is made of, how hot it is, how fast it's moving. This transformed astronomy from a science of positions and motions to a science of physical properties and compositions. Newton had imagined light as consisting of particles, tiny corpuscles traveling from source to eye. This particle theory competed with a wave theory, championed by Christian Huygens and others, which explained light as a wave propagating through a medium. The two theories coexisted uneasily for a long time, each explaining some phenomena well and others poorly. In the 19th century, the wave theory seemed to triumph, explaining interference and diffraction effects that the particle theory could not. But in the early 20th century, quantum mechanics revealed that light has both wave and particle properties, that photons behave like particles in some experiments and waves in others. Newton's intuition that light consists of particles was not wrong exactly. It was incomplete, part of a deeper quantum reality that no one in the 17th century could have imagined. His reflecting telescope design, meanwhile, became the dominant architecture for large telescopes. Refractors, using lenses, run into practical limits. Large lenses are heavy, sag under their own weight, and still suffer from chromatic aberration despite clever multi-lens designs. Reflectors, using mirrors, can be made much larger and avoid these problems. The largest telescopes in the world, from the Palomar Observatory's 200-inch telescope built in the 1940s to the modern giants like the Keck telescopes and the future extremely large telescope, are all reflectors, descendants of the little 6-inch device Newton built with his own hands in 1668. Beyond the specific content of his discoveries, Newton's approach to science has been equally influential. He insisted on careful experimentation, on quantitative measurements, on mathematical analysis. He did not trust intuition or authority. He tested ideas against observation. He developed instruments and techniques to make observations more precise. He was willing to say, "I don't know," when he didn't have an explanation, as with the cause of gravity, rather than inventing ad hoc hypotheses. This combination of empiricism, mathematics, and intellectual honesty became the model for how science should be done. He also showed the value of sustained, deep concentration on difficult problems. The Principia was not written in a burst of inspiration but through months of grueling work, solving problem after problem, checking calculations, refining arguments. His optical experiments were not casual observations but carefully designed tests, repeated with variations, analyzed quantitatively. His mathematical innovations came from wrestling with specific problems until he developed the tools needed to solve them. Genius, in Newton's case, was not just brilliance but persistence, the ability to focus intensely on a problem for as long as it took to solve it. This capacity for concentration, for shutting out distractions and working in isolation, is both a gift and a curse. It enabled Newton's achievements but also contributed to his personal difficulties. He could focus on abstract problems for months, but he could not navigate social relationships with the same skill. He could detect errors in a mathematical proof, but he could not let go of a perceived slight from a rival. The mind that could comprehend the universe struggled to understand other human beings. In his later years as president of the Royal Society and master of the Mint, Newton became a public figure, wielding power and influence. But those who knew him remarked on his aloofness, his formality, his difficulty with emotional expression. He was respected, even revered, but not warm or accessible. He never married, never formed a romantic partnership, never had children. There are suggestions from his young adulthood of some attachment to a woman, perhaps the apothecary's stepdaughter in Grantham, but nothing came of it, and after that, nothing at all. His life was devoted entirely to his work, and that work left little room for anything else. This raises uncomfortable questions about the cost of genius. Did Newton's isolation and emotional poverty enable his achievements, or merely accompany them? Could he have been a warmer, more connected person and still accomplished what he did? Or did his greatness require the sacrifice of ordinary human happiness? There is no way to know, of course. We cannot rerun history with different parameters. But the pattern is not unique to Newton. Many of the greatest creative minds have been difficult people. Isolated, obsessive, sometimes cruel, often unhappy. Perhaps intense creativity requires a kind of monomania that is incompatible with balanced living. Or perhaps we simply notice the difficult geniuses more because their personal struggles add drama to their stories. What is clear is that Newton paid a price for his achievements. The mental breakdown in 1693, the years consumed by alchemical experiments that led nowhere, the bitter feuds that poisoned his later years, the inability to form close relationships. These are not incidental details but integral parts of the story. The man who explained the universe could not find peace within himself. And yet his work endures. The Principia is still read, studied, admired as one of the supreme achievements of human thought. Physics students still learn Newton's laws, use them to solve problems, internalize the Newtonian way of thinking about motion and force. The language Newton developed, the concepts he articulated, remain fundamental to how we understand the physical world. When engineers calculate the trajectory of a spacecraft or the stress on a bridge, when physicists model the behavior of a complex system, when anyone applies quantitative reasoning to understand how something moves or changes, they are using tools that Newton forged. His influence extends beyond science. The idea that the universe is rational and comprehensible, that nature follows laws discoverable by reason, underpins much of modern thought. It shapes how we approach problems, how we think about cause and effect, how we distinguish superstition from knowledge. It supports the belief in progress, the confidence that humanity can understand and perhaps control the forces that shape our lives. This worldview has enabled enormous achievements but has also created challenges, as we grapple with the consequences of our own power and confront the limits of what reason and science can tell us about meaning, values, and how to live. Newton himself did not separate his scientific work from his religious and theological interests. For him, studying nature was a way of understanding God's creation, and the mathematical laws he discovered were expressions of divine wisdom. He spent as much time on biblical chronology and interpretation of prophecy as he did on physics, though only the physics was published and remembered. His private theological writings reveal a man struggling to reconcile his faith with his reason, deeply convinced of God's existence and governance but unable to accept orthodox doctrines that seemed to him irrational or unsupported by Scripture. This tension between faith and reason, between the truths of revelation and the truths discovered through investigation, is not unique to Newton, but in him it takes on particular intensity. He believed he was uncovering God's design, reading the divine mind through mathematics. But the universe he described increasingly seemed to operate on its own, according to its own laws, without need for divine intervention. Later thinkers would use Newtonian mechanics to argue for a purely materialistic universe, one where God is at most a distant creator who set things in motion and then stepped back. This was not Newton's view, but his work made such views possible. The irony is that Newton, who believed he was glorifying God by revealing the rational order of creation, inadvertently contributed to the secularization of thought. The more successful science became at explaining natural phenomena without reference to divine purposes or interventions, the less room there seemed to be for traditional religious explanations. This was not Newton's intention, and he would likely have been horrified by the atheistic materialism that some later thinkers derived from his work. But intentions do not determine consequences, and the world that Newton's science helped to create is one where religious and scientific explanations occupy increasingly separate spheres. As the 18th century progressed, as Newtonian mechanics solidified its position as the foundation of physics, as his methods and insights spread throughout the scientific community, Newton himself became a mythical figure, the archetype of genius, the supreme example of what human reason could achieve. Stories about him, some true, some embellished, some invented, circulated widely. The falling apple became an iconic moment, symbolizing the sudden flash of insight that reveals a hidden truth. The intense concentration that led him to forget to eat or sleep became a sign of his dedication. The quarrels with rivals were reframed as battles between truth and error, with Newton always on the side of truth. This mythologizing obscures as much as it reveals. The real Newton was more complex, more flawed, more human than the legend suggests. But the legend serves a purpose. It embodies the Enlightenment ideal of the rational individual, using observation and thought to pierce the veil of ignorance, discovering truths that transform human understanding. Whether or not the real Newton perfectly matched this ideal, the idea of Newton has inspired countless scientists, mathematicians, and thinkers, encouraging them to believe that they too might discover something fundamental, that reason and persistence can unlock nature's secrets. In the centuries since his death, Newton's specific theories have been refined, extended, and in some cases replaced. But the project he represented, the scientific project of understanding nature through observation, experiment, and mathematical reasoning, has continued and expanded. Science has explained phenomena Newton never dreamed of: electricity and magnetism, thermodynamics and statistical mechanics, the structure of atoms and the evolution of species, the expanding universe and the genetic code. Each generation has added to the edifice of knowledge, and each has stood on the foundations that Newton and his contemporaries laid. There is something both humbling and inspiring in this. Humbling because it reminds us that even our best theories are provisional, that future generations will find errors and limitations in what we think we know. Inspiring because it shows that progress is possible, that knowledge accumulates, that we understand more now than we did a century ago, and we will understand more still a century hence. Newton's work is a milestone in that ongoing journey, a moment when the path forward became clearer and the pace of progress accelerated. For those who study Newton's life and work, one of the most striking aspects is the sheer loneliness of it. So much of his most important work was done in isolation, without collaborators or confidants, often without even an audience. The plague years at Woolsthorpe were spent completely alone, developing ideas that would not be shared for decades. The writing of the Principia was a solitary marathon, Isaac shutting himself in his rooms, pushing himself to exhaustion, driven by a vision that perhaps only he could fully grasp. Even his later disputes, bitter as they were, reflect a kind of isolation. The inability to trust others, the constant fear of being cheated or misunderstood, the lack of genuine friendship or partnership. This isolation was partly circumstantial, partly temperamental. He was not good at forming relationships, not comfortable with intimacy or emotional vulnerability. He guarded his ideas jealously, reluctant to share them, anxious about priority and credit. But there was also something about the nature of his work that required solitude. The problems he tackled were extraordinarily difficult, demanding sustained concentration and creative leaps that cannot be made in collaboration or conversation. He needed long stretches of uninterrupted time to think, to calculate, to experiment. He needed to follow chains of reasoning through to their conclusions without distraction. And he needed the freedom to pursue ideas that might seem strange or pointless to others, to spend years on problems that might or might not yield results. In a way, all great creative work requires some degree of solitude. Whether you are writing a book, composing a symphony, or solving a mathematical problem, there comes a point where you must retreat from the world and engage deeply with the work itself. But Newton carried this to an extreme, turning solitude from a temporary necessity into a permanent condition. And while that enabled his achievements, it also impoverished his life in other ways. The question of what motivated him, what drove him to work so hard and sacrifice so much, is not easy to answer. Curiosity, certainly, a deep, insatiable desire to understand how things work. Ambition, a need to prove himself, to achieve something great, to be recognized and remembered. Perhaps also a kind of compulsion, a psychological need to control and master his environment through understanding, to impose order on a world that had given him so little security or affection in childhood. And perhaps, though he might not have articulated it this way, a search for something transcendent, a way to connect with something larger and more permanent than his own lonely life. In the end, he found that transcendence in his work. The laws he discovered are universal and eternal, true for all places and all times. The truths he uncovered about light, about motion, about gravity, do not depend on his personal existence. They were there before he was born, they remained after he died, and they will continue to be true for as long as the universe exists. By discovering these truths, Newton achieved a kind of immortality. His physical body is long gone, but his ideas live on, woven into the fabric of how we understand reality. There is a monument to Newton in Westminster Abbey, where he is buried among the great figures of British history. But his real monument is everywhere. In the satellites that orbit the Earth following trajectories calculated using his laws, in the bridges and buildings designed using his principles of mechanics, in the telescopes that explore the cosmos using his insight that mirrors can focus light, in the mathematical methods that scientists use every day. Every time someone applies calculus to solve a problem, every time an engineer calculates a force or a trajectory, every time an astronomer predicts the motion of a celestial body, Newton's work is present, quietly enabling understanding in progress. It is a remarkable legacy for someone who began life as a premature infant, who should not have survived, who was abandoned by his mother, who was set on a path to becoming a farmer and only through a combination of luck, talent, and stubbornness found his way to Cambridge and then to the work that would define his life. The contingency of it all is striking. If the plague had not closed Cambridge, sending him to Woolsthorpe, would he have had those 18 miraculous months of creativity? If Halley had not visited him in 1684 and urged him to publish, would the Principia ever have been written? If his mother had not relented and allowed him to return to school, would he have remained a failed farmer in Lincolnshire, his genius unrecognized and unfulfilled? We cannot know the answers to these counterfactual questions, but they remind us of the fragility of historical achievement. Great advances often depend on small, contingent decisions, on accidents of timing, on the right person being in the right place with the right resources and the right encouragement. Newton was extraordinarily talented, but talent alone is not enough. He also needed opportunity, education, time, and at crucial moments, the support and encouragement of people like his uncle William Ayscough, the schoolmaster John Stokes, his professor Isaac Barrow, and his friend Edmund Halley. Without them, Newton might have remained unknown, and the development of physics might have been delayed by decades or even centuries. This suggests something important about how knowledge advances. It is not just the work of isolated geniuses, even when it appears to be. It is a collective enterprise, built on infrastructure, education, communication, institutions, and social support. Newton stood on the shoulders of giants, yes, but he also stood on the shoulders of teachers who educated him, friends who encouraged him, printers who published his work, institutions like Cambridge and the Royal Society that provided stability and legitimacy. Genius needs an ecosystem to flourish, and part of what made the scientific revolution possible was the emergence of that ecosystem in 17th century Europe. At the same time, the importance of the individual cannot be dismissed. There are moments in history when one person makes a difference that is irreplaceable, when a particular combination of talent, personality, and circumstance produces something genuinely new. Newton was such a person. He saw connections that others missed, developed tools that others lacked, pushed through difficulties that others would have abandoned. His work was not inevitable. If he had not done it, it would have been done eventually, but differently, perhaps less completely, perhaps less elegantly. As we look back on his life from the vantage point of the 21st century, more than 300 years after his death, Newton remains a towering figure, one of the handful of people who fundamentally changed how humans understand the world. His name is synonymous with genius, with scientific achievement, with the power of human reason. Children learn about him in school, not just as a historical figure but as a discoverer of truths that remain relevant. His laws are not just history, they are living knowledge, tools that continue to be used and taught. But perhaps the most important thing to understand about Newton is not his genius but his humanity. He was not superhuman, not divinely inspired, not fundamentally different in kind from other people. He was a person with strengths and weaknesses, virtues and flaws, achievements and failures. He struggled, doubted, made mistakes, felt lonely, fought with rivals, experienced breakdowns and recoveries. And yet, through effort and insight and persistence, he managed to see further than anyone before him, to articulate truth that had eluded countless previous thinkers, to create a framework for understanding that would support centuries of progress. This is, in the end, a hopeful message. It suggests that extraordinary achievement is not limited to a special class of superhuman beings but is potentially within the reach of ordinary humans who are willing to work hard enough, think carefully enough, and persist long enough. Newton's life shows us both the heights that can be reached and the cost that might be paid. It shows us the power of solitary concentration and the price of isolation. It shows us the joy of discovery and the bitterness of dispute. It shows us what one mind can achieve and what it cannot. On that cold Christmas day in 1642, when a tiny infant struggled for breath in a stone manor house in Lincolnshire, no one could have known that this child would one day explain the motion of planets, reveal the nature of light, and create the mathematical tools that would unlock countless mysteries. That future was unwritten, dependent on countless choices and chances that had not yet occurred. But the potential was there, in that small, unlikely form, waiting for the right circumstances to unfold. And unfold they did. Through abandonment and loneliness, through years of study and years of isolation, through frustration and breakthrough, through conflict and triumph, Isaac Newton's life traced a path from that manor house to Westminster Abbey, from obscurity to immortality. He changed the world not through power or wealth but through understanding, through the careful, persistent application of reason to the mysteries of nature. He showed that the universe is knowable, that its laws are written in the language of mathematics, and that human minds, fragile and limited as they are, can nevertheless read and comprehend that language. The work continues. Science has moved far beyond Newton, exploring realms he never imagined, using tools he never dreamed of. But it moves along paths that he helped to clear, guided by principles that he helped to establish. Every spacecraft that reaches another planet, every bridge that stands firm under load, every prediction of an eclipse or a planetary position that comes true, all of these owe something to the work of a solitary, difficult, brilliant man who spent 84 years trying to understand the universe and who, in significant measure, succeeded.